I think we have a real treat in front of us to hear from the industry perspective about energy storage. And so without further ado, I'm going to introduce my colleague Craig Arnold, who knows much more about energy storage than I do.
Thanks, Emily. So thank you all for coming. It's a great pleasure to have Mark Verbrugge here giving us a talk. Mark is the director of GM's Chemical Sciences and Materials Systems Laboratory. And they do all sorts of global research programs. So it's not just batteries and energy storage, but really a lot of the material science, chemistry, and physics that's involved in automobiles and manufacturing. Mark is a very distinguished member of the academic research community, not just the industrial world, winning a number of awards, many, many publications. Most notably, Mark is a member of the National Academies of Engineering, which really is a testament to the sort of the level of academic and research excellence that his group has done over the years. Personally, I've known Mark's work from his work on mechanics of energy storage systems. Really, his group is responsible for some of the really fundamental knowledge that's involved in understanding how lithium batteries behave when lithium intercalates and deintercalates, and how that plays out over time. And really, it's been a lot of the work that we've built much of the research in my group off of, sort of trying to take it one step further. And so today, Mark is going to be telling us about vehicles in general, some of the role of coatings and other thin films used in these types of energy storage systems. And Mark, please.
Thank you, Craig. And Emily also for the invite here. It's really an honor to visit Princeton and be able to give this talk and see some of the faculty and the great work that's going on. So just a very brief outline of what I'll talk about. First, I'm going to provide some electric and hybrid vehicle pictures, basically, and description of vehicles, and hopefully that's motivational for what's going on. Also give you a sense check of what's contemporary in the industry in this regard. And then I'm going to look at Gen 1, Gen 2, and on to Gen 3. And what I refer to in the context of Gen 1, it's one that's on the road right now. Gen 2 you might think of as the next 5 to 7 year time frame, next product life cycle. And Gen 3 would be beyond that, so 10 years out or so. And hopefully this will be useful information I'll summarize. So in terms of motivation, and I'm not going to dwell too much on this because you're all aware of this, and certainly the Andlinger Center is going after this issue as well, but you could plot almost any commodity you want. On the ordinate plotted here is ownership per 1,000 people for vehicles, for personal transportation, and then you have per capita income on the abscissa, and it's a monotonic curve. You kind of wonder what Canada's doing, but otherwise it's, generally shows a trend. Now there's something else that's overlaid on this plot, and that's the green circles and the red circles. And that's going to be key when we go to the next slide, but you can kind of see the red circles are developing, so-called developing markets. They're down near the origin, and they're moving up over time, of course, into where the green circles are today. And so it brings into the question of sustainability. So with that in mind, it's kind of an interesting chart to look at. It's vehicle sales in millions on the ordinate in the different countries, and then time is denoted by the different colors. So for any group of bars, say India here, this would be 2000, and then up years coming up to 2011 when the last data for this slide was taken. And I put in some bars or some dotted lines to kind of show you trends, but what you can see is the areas where it's hyper competitive, it's really hard to make money, are Europe, Japan, and the United States. These are very mature markets. They're actually declining in terms of vehicle sales. The other thing to note is that the emerging markets now actually outnumber, you can see the 39.5 million sales versus 36.5 in mature markets. So we are selling more vehicles into emerging markets. Actually, automotive in some respects is a great business to get in. It's growing at about 12% annually. But of course, the growth is outside of these mature markets. And so that makes it so you wonder, what are people working on for vehicle design? A lot of our work, like in GM's case, as of about 3 or 4 years ago, we were selling more vehicles outside of the United States, or outside of North America, I should say, than within North America. And so a lot of the design and construction of vehicles and thought about who the customer is actually reflecting emerging markets in many cases today. So with that in mind, I'm going to start from the most mild expression of vehicle electrification, start-stop, and work my way up to a pure electric vehicle and let you know what's going on in the road. So this is a product that we have out there today. It's actually marketed for all of the brands, all the major models for Opel, and that's because Eurostage 6 kicks in sooner in Europe, and so we came out there first with our start-stop systems. Now, start-stop systems, I think, are going to go through a revolution, so to speak. Right now, they're lead-acid batteries, and our highest warranty item in all of automotive has this issue. In hot weather climates, so in the United States, that would be in the Southwest, like Arizona, is the lead-acid battery, the starting, lighting, ignition lead-acid battery. So the number one warranty item in terms of cost for General Motors. When you start hitting the lead-acid battery with more and more starting events, that situation is going to be exacerbated. So what's done now is to go to a two-battery solution, a two lead-acid battery solution. And there's still a big concern over warranty for these types of vehicles. My thought is if I was going to pick my favorite material, it would probably be an LTO, lithium titanate negative electrode. It's a so-called zero-strain material. So when you put lithium in and take it out, the host lattice hardly changes at all, hardly breathes. It's an open three-dimensional spinel structure, and lithium transports quickly in and out of the structure, give very high rate operation. Arguably the best positive electrode that is fairly low cost would be lithium manganese oxide. It's also a three-dimensional spinel network. It is a very fast diffuser, so to speak, of lithium, and I could see where that could come on. Cost will be an issue, but I think these things will come to life of the vehicle solutions, and the lithium systems, dual spinel system will work out quite well there. Going on to the next form, this is a stronger hybrid. In GM's case, we refer to it as e-assist. It's about 15 kilowatts, so it has regen capability. It has opportunity charging. So when you're driving the engine and driving the car on the highway, for example, and you're in the sweet spot for efficiency, you might want to charge your battery at that point in time. And other times you want to modulate where you're doing the charging and discharging from, whether you're using the heat engine or whether you're using the energy storage device. Actually, what happens in all these hybrid vehicles, so vehicles stronger in hybridization than this and this vehicle, is the hybrid system controller is doing a fuel economy calculation at every time step and trying to figure out if the driver continues driving like they have been driving, what should you do in order to optimize fuel economy? And that's basically what goes on. Now, to do that, you need to have a good model of the battery. And you are running an adaptive control scheme. We use a Kalman filter and we use a battery model. And we identify the state of the battery, try to figure out how much power it has available and how much energy it has available. These already exist for heat engines. And so from that, once you know the states of your system, you can then decide what's the most efficient thing to do at the next time step. So that I should back up. That has an amorphous carbon. Amorphous carbon is very good for high-rate lithiation and delithiation compared to, say, graphite, the well-ordered carbons. And so in hybrids where I think I might have lost my sound here, but where you're going after power, you typically see amorphous carbon, whereas in high-energy systems, I'll show, we use then typically graphite electrodes. So the e-assist is coming out mainstream. This is kind of important because when we're trying as engineers and researchers trying to drive technologies into vehicle systems, until you actually get a dedicated platform, it's very hard to do. So the only Buick Regal you could buy had hybridization in it. You knew that you had a ready customer there, and the decision had been fully made, and your platform was fully behind you as far as the commitment for that. There are a number of vehicle platforms now committed to actually this e-assist system, so you can see it going much more mainstream across GM products, much like other companies are doing as well. Next step up in electrification would be the Chevy Volt. It's shown here. Some of the attributes are displayed. This uses a very similar system to what we saw in the e-assist, but instead of just NMC, it has a spinel component to give you high power capability on the positive electrode. This battery has to have both high energy density and high power density because for the first 40 miles of the drive cycle, it is a full function electric vehicle. The heat engine does not come on. And then after you've driven that electric vehicle range, then you have a charge sustaining hybrid after that with the remaining battery state of charge at nominally about 30 to 35%. Oscillating about that value to the rest of the drive event. And then graphite is on the negative electrode. And we have announced other vehicle programs with the same technology. The Ampera is already out in Europe, and the Cadillac ELR will be coming out. So the strongest version then of electrification would be a 100% electric drive, so an electric vehicle, a battery electric vehicle. In GM's case, there's a competitive product out there. When I say competitive, it's much like what other car companies are offering in this segment. One thing that's kind of fun about electric vehicles is that they actually have very good torque because electric machines have max torque at 0 RPM, and so the initial acceleration is very good on electric vehicles. We used a graphite lithium iron phosphate on this system in part because it's level 3 charge capable, so it has rapid charge capability. The iron phosphate is very good at high rate operation, and it then confers this capability onto the vehicle. So those are some of the vehicle programs we have out there. It's still the case that massive or widespread electrification across the vehicle fleet, other than StartStop, which I think will go across the vehicle fleet, is not there, and the remaining challenges are mentioned here. It's basically cost and performance for the customer. So these are things that researchers are working on hard today, and there's been a lot of progress. I'm not going to talk too much about some of the metrics you might use. We could do things like plot cell costs as a function time or what have you, but by and large, there's been very good progress being made in these areas. What I am going to do is talk a bit about some of the technical challenges, and to do that, what I'm going to do is talk about Gen 1 first. What you're most concerned about in Gen 1, because we know these things offer value. Customers like what they get out of a lithium-ion, say Chevy Volt. Other than cost, that's a challenge, but otherwise it performs well, and what you worry about then is life and warranty. So that's something we've got to worry about today, and I'm going to talk a little bit about what are the life mechanisms for current batteries, and then we'll go on to Gen 2 and Gen 3 after that. So in terms of this Gen 1, Gen 2, Gen 3, in the positive electrode, so cathode on discharge, in the green box, you can see a number of systems there. Those which don't have an asterisk are basically Gen 1, what we're using today, layered oxides, for example. The second one up there, the complex, starts out with complex. That's the high energy NMC variant that we probably will see in a Gen 2 timeframe, perhaps Gen 3. I mentioned the spinels and start-stop. High voltage spinels, it's a different variant where you now have a manganese nickel spinel system. You operate at about 4.8 volts there. The challenge is to get a high voltage stable electrolyte. You'll see down here, high voltage stable electrolyte system is something that's still out there that hasn't been developed. As you come down into the negative electrode, the anode on discharge, carbon is the standard today. It's silicon composite, and alloys of silicon are likely going to be coming out in the near term, so Gen 2. And I think the rest of the slide is pretty much self-explanatory. So that sort of gives you maybe a thumbnail sketch of what's going on from a materials point of view. If I were to sort of stand back, using green, yellow, red for red is green, yellow maybe Gen 2 will be green soon, and red is stuff that we don't really know. This is my view of what's going on in this landscape. Cost is labeled on the ordinate, and today we're at about the $300 to $400 per kilowatt hour cost, depending on the technology, depending on what your power to energy ratio is as well, and that goes to the application. Next gen, I talked about this Gen 2 and folding a bit into Gen 3. And then there's a DOE target out there. It's actually $125 per kilowatt hour at the battery pack, and you can roll it down if you're being aggressive about pack cost not being too excessive relative to cell cost to about $100 a cell. And this is so-called, I've called it Horizon technology or Gen X. We don't know how to do that right now. And that's what I would call, it even goes beyond Gen 3 actually to get to $100 a kilowatt for the cell, kilowatt hour. So Gen 1 and Gen 2 lithium batteries, I'm going to talk about life and performance as I sort of set up earlier as perhaps the most relevant aspects of what we need to worry about today. My son made this up for me at one point in time. It's when I first learned about cartooning on PowerPoint. But it helps to say, when we say here's what a lithium-ion battery is, I know the audience is pretty diverse here, so I want to do a couple slides that go to sort of the basics of a lithium-ion battery. And I'm going to be kind of spotty as far as sometimes it'll be introductory type material, and sometimes it's going to get very much into a technical path, and hopefully the balance will be acceptable. But as a lithium-ion battery is made, initially the lithium is housed in the metal oxide. That's going to be important. I'll talk about in the next slide. And then you have an electrolyte phase. This isn't drawn to scale. This is typically about 50 to 100 microns in thickness. It's a porous electrode where you have inside of the active materials vacancies for lithium that can be filled. This is about 25 microns thick, the electrolyte phase. The yellow would represent solvent, typically diethyl carbonate and ethylene carbonate today. And the lithium ions, lithium hexafluorophosphate phosphate are shown here. Lithium ions then move across to, in this case, the charge reaction to fill the negative electrode, the carbon. And so the reverse reactions happen on discharge. The lithium just comes back to the other side. In fact, when these batteries were first developed, the term rocking chair batteries was used because the lithium rocks back and forth. You might think, well, why would lithium move? Why does it spontaneously discharge from this electrode to the other electrode when it's full? And the answer is it's the chemical potential difference. The chemical potential of lithium is different in the two host materials, and for that reason it spontaneously discharges when you've charged up the carbon electrode. So these are some of the dimensions that I talked about earlier, and if you sort of drill down then into the porous electrodes, you get these particles. The particles are about 5 microns in diameter. Sometimes they're as large as 10 microns. And then if you dig into the graphite particles, you have this layered structure of about 3.5 angstroms between the graphene layers. You have sort of a similar structure for the metal oxides. It's different for iron phosphate, a one-dimensional material, and there are some other materials out there, but nominally you can think of this kind of cartoon as far as understanding how these systems work. Now, when you first construct a lithium-ion battery, you use an excess of negative electrode, and that's because once you've filled the carbon electrode, the next reaction to occur when you keep on reducing lithium to fill up the electrode would be lithium plating. Lithium is extremely reactive. It's 3 volts negative to a hydrogen electrode. It's an extremely reducing atmosphere. It rips up the solvent, and you generate gases and you generate unwanted products, and it becomes a hazard, and it's also inefficient for your system. So you always want to have a little bit of excess negative electrode. So this is, I think, a key slide if you're going to understand the next portion of the talk, and that is how do you actually design a lithium-ion battery? And I've tried to put it schematically to help out in this manner. The bullet, and I made the slide up last night, so I'm hoping I don't have typos on here, but at any rate, I was thinking about the talk and trying to see how it might go a little better if I gave this introduction. In the initial condition, you have this figure over here. After you've conditioned the battery, no automotive manufacturer gets a battery that hasn't been cycled by the supplier of the cells. In GM's case, for example, we buy the cells from our suppliers, and then we integrate the cells into a pack and into the vehicle. So initially, you have all of the lithium in the positive electrode material. That's an air-stable material, so you can assemble cells in a dry room. It doesn't have to be a clean room. That's important. I make the note here about double-layer capacitors. A lot of people thought we'd be using more electric double-layer capacitors than we are today. One of the big problems there is they have to be hermetically sealed, just like lithium-ion batteries, but they also have to be assembled in an argon or inert atmosphere, and that's proven to be very expensive. So even though the raw materials, carbon, are cheap, although they have to be prepared and etched at high temperature and cleaned, the assembly process is extremely difficult in that inert environment, and it's been one of the limiting issues for that technology to go mainstream. Now, when you discharge the cell, you put all the lithium from that positive electrode into the negative electrode. And I mentioned you have an excess of negative electrodes, so you don't get lithium plating, so you never utilize all the negative electrode. After you cycle the cell, or if you just let it sit, there are degradation reactions, very slow. That's why lithium-ion batteries basically are life of the vehicle. The Chevy Volt, for example, has an 8-year warranty on the battery pack, and it should last much longer than that. But you do get gradual degradation, so that end of life at about 75 to 80% of initial capacity, the lithium content in the positive electrode, when you're fully charged, is you've left over some material. What we find in, this is why I call it preferred wear-out mechanism, is the host materials have not lost any sites. They're still available. If you take the cell out, cycle in a separate half cell, you find out that host material could cycle lithium just as it did initially. What's happened is you've consumed lithium in the cell. And that's where the life modeling comes in, I'll talk about. When you then, near the end of life, when you then charge up the battery and put the lithium over into the negative electrode, it just rocks across and it fills up. And again, you have a lot of negative electrode that's not used. This orange is the separator. So now we're going to go on to some life modeling aspects. And whenever you talk about life, it's helpful to talk about quality. So you have, in terms of a classic bathtub curve, number of failures plotted on the ordinate, early infant mortality failures down here. The usable life is the middle portion. And what I'll talk about is over here on the wear-out side of things, where you start to see a battery wear out after nominally about 10 years or 1,000 cycles or so in an EV type situation. Now, you can, loosely speaking, try to deconvolute these processes into saying counter life. That's a chemical degradation reaction, which I'll talk about. So if the battery just sits there, it's going to chemically start to degrade and consume some lithium. And then you have cycle life, and this gets into the expansion and contraction, formation of cracks, new surfaces. They get passivated by the chemical reaction from up above, so it is coupled in that respect. But you can argue that mechanical degradation is nominally related to cycle life more than counter life. Obviously, if something's just sitting there not cycling, you don't have a cycle life dependence. I like to use this particular publication when I talk about the irreversible chemical reaction that occurs, because we were using at that time for a high-power device that we were working on for applications, carbon nanofibers, rather large to use the term nano, but the high surface area gave rise to exacerbating or making clear the chemical reaction that goes on. That's the degradation reaction. So on the very first cycle, when you condition a lithium-ion battery, what you find is this is a carbon electrode versus a lithium reference electrode. So this is the potential of the carbon versus the lithium reference electrode in a cyclic voltammeter experiment. You scan the potential linearly at 0.1 millivolts per second, no lithium in the carbon. And then you come down to this reduction peak at about 0.75 volts versus the lithium reference electrode. And that reaction, I'll talk about on the next slide, but it's a solvent reduction reaction. You generate a bunch of bubbles. You see ethylene gas coming off. You're destroying your ethylene carbonate, liberating ethylene gas. And then you get down to this region where now you are actually inserting lithium and then deinserting lithium. So that's the reaction you want in the battery. And then you come back, we've taken all the lithium out. You've deinserted it all. Look at cycles 2, 3, and 4. You can't even see any evidence whatsoever. That's the beauty of a lithium-ion battery. This solid electrolyte interface forms on the surface, and it passivates subsequent reaction. Now, that's kind of part of the story. And this comes from, this is the same reference as before, but after you start forming the carbonate as an inorganic inner layer to form this film over the surface, you start generating these lithium adducts afterwards, these organic layers, and by FTIR, the general reaction that is accepted as most common is listed up there. So that reaction is actually occurring at that same voltage in what I've called now, that's cycle 0 where we have the conditioning, but cycle 1, cycle 2, and cycle 3, it's still occurring. Just at such a low rate, it's hard to measure it. The current efficiency is very, very high. And it's kind of like a compound interest problem if you figure out why this is important. Think of starting out at cycle 1 in the far right corner with amp hour naught, the nominal specified amp hours. And then after your first cycle, you're going to have a current efficiency, let's assume the current efficiency is constant, of eta sub I. Say it's 0.99 for now. And then you can walk down, and each cycle you keep on losing some capacity. In fact, you can get a very simple formula, number of cycles, amp hours naught, current efficiency, and number of cycles shown up here. So you can solve to say, okay, if I want, for example, in a Chevy Volt application, we need 5,000 cycles. And I don't want to go less than 75% of my nominal capacity. What's my current efficiency have to be? You find out it's got to be super high, 0.99994. And that's why you can't see anything there, but that reaction listed up there is consuming lithium. And so just as I drew in that little schematic before, you're consuming lithium, you lose it. Your host materials are still active. They still have sites available for lithium. You just don't have lithium to go in them because you've consumed it by this SEI reaction. It's ending up on the negative electrode surface as inert solid electrode interface and other junk that forms at the surface. So there are people out there today, I pulled a couple slides here from some of Jeff Don's publications with some of his colleagues at Dalhousie that are making now very high precision coulometers. And the hope is that we could actually do accelerated life measurements if the instrumentation industry came along and delivered these systems. It's very hard to get that kind of high efficiency. You can with special precautions, and that's what this group, the physics group at Dalhousie, has been doing. So I've talked a bit about degradation. This is a sort of a pictorial explanation of it. Starting on the left, we have expansion and contraction, so solid mechanics play a large role there. And we find that the stresses on discharge are very high at the surface, the tensile stresses that tend to crack then the particle at the surface. And what can happen then at a blow up, you can see here these cracks start to grow in. And anytime you have a newly exposed crack in that carbon electrode, the negative electrode, you start to go through these passivation reactions to form new SEI, and that's lithium consuming, and that presumably is why you're getting continual lithium consumption as you cycle these batteries. Now, this was a very simplified model. It was actually for a low-rate charge and discharge commensurate with an electric vehicle battery. And when you make those assumptions, you can make some asymptotic expressions work for you and come out to a closed form solution that's shown here for on the left-hand side. I won't walk through this, but left-hand side is the fractional capacity. So initially that quantity is 1, and it's going to degrade from 1 to, for example, in the volts case, we go down to about 0.75. And factors that show up are things like the maximum tensile stress at the surface, and that turns out to be, and I don't have all the parameters showing up here, but you'll see things like modulus of material, Poisson's ratio, those things you expect to see from solid mechanics as you expand and contract a particle due to concentration gradients that are in the particle, just like thermal gradients give rise to thermal stresses in thermal elasticity calculations. And we use Paris law to try to track crack growth. It's a very empirical approach. It's from an energy balance. I would argue it's acceptable because people publish volumes on Paris law constants in material science. But that's where we are right now as far as state of the art in modeling of these systems. My feeling is that there wasn't a previous publication before this one that coupled something like Paris law or some other method for a crack growth, crack propagation model, and then diffusion-induced stress, so you're solving your transport equations for lithium solute inside of the host material. and then the chemical degradation that occurs at the surface, so those chemical kinetics. Those are combined in this model to try to map out the life characteristics. And so here's some comparisons with experimental data. Fractional capacity is plotted on the ordinate versus cycle number for 3 different temperatures. So just as an example, if you take this lithium iron phosphate, lithium graphite cell, and you cycle it you get about 500 cycles, and 86% of the fractional capacity results after 60 degrees centigrade for this system. And you can see the trends for the other temperatures. Obviously, lower temperatures are better. There's an Arrhenius dependence of these rate constants on the reactions, especially the chemical reaction rate constant, and that tends to play a large role as far as the degradation goes. Now, that was a really simple model. And I mentioned that you can get some asymptotic expressions because it's very low rate. That helps. When you discharge an electric vehicle battery, you drive at least an hour. But the time constant for lithium to diffuse within these small particles is on the order of 30, 40 seconds. And so that's why we could get these very simple expressions to come out. Turns out that when we looked at lithium diffusion and transport in graphite, it's a lot more complicated. And that's what some of these slides are mentioning. But what we wanted to say was, look, graphite is actually, fundamentally, if you say graphite, that's a multi-phase material. You have different stages. People who study carbon and solutes in carbon or lithiation of carbon refer to them as stages. And a metallurgist might refer to this as a multi-phase and grains in these systems. But at any rate, so they have this multi-phase behavior. And the Gibbs phase rule will tell you that if you have 2 phases present and constant temperature, you're going to get a voltage plateau, which is indeed what you see with graphite. You have these voltage plateaus in graphitic materials. But the fact of the matter is, we never have perfect graphite in our cells. And after we cycle them for a while, we got all kinds of dislocations, and you never see perfect 2-phase behavior. There's always some slope when you look at these systems. So my thought was, let's take advantage of this fact that it's somewhat disordered, it's not perfectly crystalline, and let's try to treat it as a pseudo single-phase material. And what that means is to use irreversible thermodynamics on a single-phase material, and I hope this will become more clear. So I'm going to take one digression. When I first went down this path, it was for disordered carbons, and so there you don't have this argument. These are largely single-phase systems. You can see this by a sloping open-circuit potential curve, which is very similar to a sloping free energy curve versus composition. And so here are experiments for cyclical photometry at 10 millivolts per second for a lithium single fiber electrode. There's some schematics of the single fiber shown up in the upper right. We address a single fiber and use it in a beaker, and we can do electrochemistry on it and not be inhibited by binders or conductive diluents or other things you use when you make a porous electrode, so you can get a little bit more robust as far as how these things are working and study the materials themselves. The theory is shown on the right, and the reaction, I've already talked about it over here. This is just another way of writing it. The lithium comes up, reacts with the host, and inserts. From the open circuit potential, you can actually deduce the chemical potential of lithium. And so if it's unsubscripted here, no subscript means it's referring to the lithium species. This is lithium in the reference electrode. So in this case, it's the metallic lithium electrode. If you use irreversible thermodynamics, our flux expression looks like this. This becomes Fick's law if you're infinitely dilute. If you're not infinitely dilute, you end up with this gradient in the chemical potential showing up. And when you stick that flux expression into your material balance equations, you get this expression over here for the lithium mole fraction X, and we have an effective diffusion coefficient showing up here, which would be including all these terms. And what's important to note is this quantity you can get from the open circuit potential. It's a thermodynamic quantity. You don't need to redo it after you've measured your open circuit potential. Some people try to model open circuit potentials by things like density functional theory as well, and you might have a connection there in length scales for solving these problems. Now, if all goes well, this whole effective diffusion coefficient, which I've written down here, simplifies to, when you're at infinitely dilute systems, the activity coefficients that come into these expressions go to unity. You get Fick's law. So infinitely dilute, you get the infinite dilute diffusion coefficient. And then everything else inside of here is easily computed. This comes from the open circuit potential, Faraday's constant over gas constant and temperature, mole fraction of lithium. It's nonlinear, but everything is available to you. You don't have to introduce any new information. And that worked quite well in this single phase system. So my thought was, let's apply it to graphite, and hopefully we can go right to the open circuit potential. I'll show an open circuit potential curve in just a minute, but it has this disordered nature that provides the energetics for this du by dx term. So when we were doing this, what we found is we started computing, this is case A above, based on this open circuit voltage that we differentiated, computing these diffusion coefficients. So over here it's the normalized diffusion coefficient, normalized by its value at infinite dilution. And they were sort of bizarre looking. I hadn't seen anything like this myself. And so that was kind of worrisome. There were people out in the literature who were fitting diffusion coefficients simply to existing data by, in this case, Takimi et al. And you can see the diffusion coefficients varied by 2 orders of magnitude. Now, if you're doing mathematical modeling, you're trying to do vehicle design and integration, if you've got a key parameter in there and you're limited by solid-state diffusion, that parameter varies by 2 orders of magnitude and you don't really understand why, it's difficult to say you actually have a model at that point in time. And that's why we wanted to work on this problem. So it was just amazing to me when I saw this publication later by Arbach, and it was an older publication, I just hadn't been aware of it, where they had taken some very careful PIT data, potential static intermittent titration technique, and the symbols are their data, the blue lines are drawn through their data, and the red curve shown here is actually the blue curve over there, but you can see it matches up pretty well. And the idea is that the irreversible thermodynamics that comes from the open circuit potential embedded in the transport equations gives rise to a diffusion coefficient, an effective diffusion coefficient, that looks a lot like what people measured. And last, what you can do is, you can see it in that top expression over there, you can actually integrate du by dx. So integrate Arbach's data, Arbach, Levy, and Levy, and you can then calculate an open circuit potential. And that's what this red curve is. You're actually taking the transport measurements and back calculating a thermodynamic quantity, because we didn't have their open circuit potential from their paper. And in fact, when we did the model to get this, we took some open circuit potential data from some work I'd done earlier on Lanza graphite and hoped that that graphite was close enough to what Arbach and folks had, and we got something that was kind of similar to what they had. So here you can see, this looks just like, for those who work in this field, looks a lot like a graphite open circuit potential curve, and sort of validates this notion of going back and forth. So my point is, we were very fortuitous in that counter-life modeling. We had parameters in there that we were juggling to try to make it fit the data. It looked like it fit the data pretty well, but obviously transporting these multi-phase materials, or transporting graphite, is a lot more complicated than a dilute solution treatment. So with that, I'm going to go on now to Gen 3 systems. And one thing I just would mention is a lot of these Gen 3 systems use metallic lithium negative electrode. And Peter Bruce wrote a paper where he's looking at some of these different systems, and the architectures are shown up at the top, starting at the lithium-ion conventional today, and then lithium air of various types coming across, and lithium sulfur. All of them are using this lithium metal negative electrode. And in GM's case, we funded a fair number of programs joint with the Department of Energy, Ford, and Chrysler on sort of high-risk endeavors that used lithium metal electrodes, and this was about the 2003 timeframe. It's pretty tough. It's a pretty challenging area. No one ever made it work, and 3M Heidelberg had a large effort in this field as well that was funded by DOE. Within GM, we actually went down this path as well. GM used to have Delphi, the components group, and so they had a lithium-ion battery starting about 1992. And for about 2 years, we were using lithium metal, and that came to be problematic. And eventually, Delphi was split off, so it ended up that we didn't go too far down this path together. But what I would say is, when we were doing that work, we tried to do some work that was allowed us to understand how these systems were behaving. And I'll show you the results in the next slide, or next couple slides, as to what happened here. But when you look at lithium itself, just the lithium reaction, what you find is that it's actually, as you'd expect by Marcus theory or by people who have looked at electron transfer reactions, a classic electron transfer reaction, and that it is extremely fast. Now, lithium is a very light element, obviously, and it has one electron transfer. It's well solvated, and so it has a perfect in the sense of a 0.5 symmetry factor. It's very symmetric to charge and discharge reactions. And for those who work in this field, there's an equation, the Butler-Ballmer equation, that's often used to model interfacial phenomena for charge transfer reactions, and it works out quite well that way. And you can see the exchange current densities that are backed out from this system are extremely high. 300 milliamp per square centimeter at 75 degrees C, that's an enormously high value. So you could say there's a lot of promise in using a lithium metal negative electrode, because real fast kinetics and well understood. The problem is, if you just take, this is a micro disc electrode, and that allows you to actually, I won't go into that detail, but it allows you to access more accurately electron transfer reaction rates. If you take the micro disc electrode, you deposit a little bit of lithium, and then you just wait. In this case, we wait for 0 time, 180, 360, 540, and 720 seconds. And after our wait period, we strip off the lithium. You strip it off over here, and you get a fair amount of material out. And the longer you wait, the less material you get. It's reacting. It's just reacting right away. It's reducing the solvent. And that's the problem with the lithium metal electrode. It's extremely reactive. We don't have a good solvent that, adjacent to a lithium metal electrode, shows sufficient stability. Now, one other aspect to those who deal with problems of crystal growth and nodule formation is that you do run into a paradox in a lithium-ion battery, and that is that they're actually fairly resistant, the electrolytes. And for that reason, we have to go to a thin film arrangement. We have this 25-micron thick separator. The non-aqueous electrolytes are about almost 2 orders of magnitude less conductive than, say, a sulfuric acid electrolyte used in lead-acid batteries to start a car at very cold temperatures, minus 30 degrees C. So at any rate, we go to a thin film geometry. If you have a protrusion, like on a metal electrode, and you bring your electrodes closer together, you will focus more growth on the tip of that protrusion. You exacerbate dendrite growth or nodule growth. And for that reason, there is a paradox out there that the more you push your electrodes together to get a thin film, the worse it is for your shorting by metallic shorting across the cell. And that's something that will always be a challenge for a lithium metal electrode in particular. So for those reasons, we did this study where we convinced our management within General Motors that we ought to switch from lithium metal to lithiated carbon. That was about 1993. This was a piece of data where it's a cyclotamogram, again, on the same single fiber electrodes that are used as active materials in lithium-ion batteries, one form of active materials for graphitic materials. And so we have potential being scanned in a triangular potential source here. We're measuring the current. This is lithiation, delithiation. So the lithium's coming, it's lithiation, charging the electrode, and then delithiation at the top, taking the lithium back out. And over here, you'd eventually come to the point where you have no lithium in the system and your potential is more of an oxidizing potential. The point is this was recorded on an oscilloscope. It's 300 cycles. It's just rock solid. The cycles plot over one another. And is what we use to convince management the active material works. And the reason I thought it might be helpful to put this slide in here is that I think when researchers come into an industrial research setting, especially new researchers, it's important to keep in mind that very simple, very fast experiments can be used to make significant decisions. You don't need a whole bunch of development dollars. And it's usually just a faster way to go. A lot of companies instead went down that lithium metal route. There was never a solution, and they start working on the cathode. They're working on a whole bunch of other things. The big rock in the road was the lithium metal electrode. And here you could more or less see that, and you could remove the problems of the lithium metal electrode by going to a carbon material. So going on now more into the Gen 3, the reason there's a motivation to look at these systems, obviously high energy density. If you look at all the elements in terms of negative electrodes for materials, we're out here at about, theoretically, 372 milliamp hours per gram of host carbon for the current technology. Real systems get about 320 to 340 milliamp hours per gram. Silicon just blows it away. It's 4 times higher. The challenge is that with silicon and many of these other systems, tin as well, basically the more you put in there, so the higher energy density your cell gets with these negative electrode materials, what you see is greater and greater expansion to up around 300% for the silicon system. You get enormous stresses built up in your particles, and all of those cracking and other phenomena associated with new solid electrolyte formation become something you've got to manage. And there are ideas for that I'll touch on just a bit. So with Brown, we did some work on trying to measure stress in these systems. One of the things we did was to look at thin film, so we get a size effect here. We're going to go to very thin, 75 to 100 nanometer thick film, so we have some adherence to the substrate. And we put in stress relievers between the pads. These are pads of silicon on a otherwise inert substrate. And then we measured the stress, and I'll talk a little bit about that. So one of the things that you see in silicon electrodes, a pure silicon electrode shown here, is you get this pattern of crack formation where it looks like the cracks are forming about 7 micron characteristic dimensions. You almost can think of pads of active material with stress-relieving cracks around them. And that's partly why we decided, well, let's put in different pad sizes, but we'll terminate with a 7 micron pad and see if we can actually get enhanced cycling capability. Now, this is just addressing the mechanical degradation. There's also chemical degradation that this work doesn't address because we're using a so-called half cell. We have lithium metal opposite our lithium silicon. So there's plenty of lithium metal. You never have a shortage of lithium like I was talking about for life in a lithium-ion battery. You have plenty of lithium there, and so you don't see that effect of the chemical degradation. So there are techniques. This is a classical Stoney equation to measure basically the stress, average stress in your system, and it's an optical measurement. And what we find is that if we use a continuous film, and again, these are about 75 to 100 nanometer thick films. We get this, we have the voltage shown here for constant current, in this case charge and then discharge, and you see that this stress profile mimics it, and this is basically a flow stress here. We're now seeing flow, and so we don't see it go down in a sharp manner. If we instead go to the patterned electrode, and this is the 7 micron pattern, what we see is it's basically elastic. It comes down, it goes back up, it's very reproducible, and so you can infer from that that when things start to go into plastic deformation is when you start to run into problems as far as mechanical integrity, and you actually lose. What happens is we find out you lose those electrode pads. They detach from the surface if you have too much degradation or too large of pads. And you can actually do a very simple force balance on these systems, which is one of the things we did. And there are some published values independent of this work for the yield stress of silicon and the interfacial flow stress for silicon over copper. And what you find is, fortuitously, you come out in about the 5 to 9 micron region, which is quite surprising. We were at 7 microns and we saw good stability. The point is, you do get a size effect in these systems. Now, remember, we're dealing with very thin films. If we had thicker films, now we'd have problems in our dimension normal to the film as well for stability purposes. The last thing I'll mention on thin films that is, I think, helpful is that there are techniques, in this case, potentiostatic intermittent titration technique. I'd mentioned it earlier for what Arbach and folks had done. We used it on a thin film of silicon. It's a very nice way to characterize these electrode materials. And you can get a short time and a long time solution. And this is by solving for a slab geometry, the diffusion of lithium into the slab material. PIT, by its nature, it's small-scale potential excitation. You use about 5 millivolts. Because you use such a small scale for your excitation, you can linearize your transport equations and your whole system of equations, and you get analytic solutions. And you don't need to worry about variations of the affected diffusion coefficient, that term I showed earlier, in terms of intruding on your transport equations, because you're linearizing about small fluctuations in concentration. So here we see on the left the current versus 1 over square root time, and for the short time solution. The long time solution, we had basically the same values for the Biot number that we fit to it, this ratio of resistances, diffusion to interfacial kinetic resistance. One of the key points to this that you can get out of this type of analysis, because now you're measuring a property of the material, is diffusion in lithium in these silicons that are of interest for electrode materials is about 3 times less than that in graphite. So it's going to be a challenge to get the power out of these systems. That leads to a whole other way you might architect batteries in order to make them viable for electric vehicle applications. So the, let's see, I probably should be wrapping up here soon, or do you?
No, you're fine.
Oh. Okay, 10 minutes is probably more than enough then. So what I would say is, this is a figure I showed earlier, and I mentioned that if you look at the effect of a constant current efficiency, you need a value about 4 nines to get 1,000 cycles, and it turns out if your current efficiency is about 99%, you'll get about 23 cycles. The reason this is important is a lot of researchers will publish work on silicon. They'll say, well, you know, the current efficiency is pretty high, it's about 99%. Well, that's not good enough for these systems, because 99% is not going to get you anywhere near what you need to have actually for an application. So that's why I sort of insist current efficiency should be plotted on a logarithmic scale, but you certainly should be looking at high precision coulometry, I would argue, for these systems if you're looking to close that last step and understand whether the chemical degradation is important or not in your systems. So what are people doing to try to make these systems work? There's a lot of work on core shell structures, and this is just one piece of work that the title of the paper, if I remember correctly, I don't mention it down here, but it was concerned specifically with different core shell structures. In this case, they showed in particular a tin system. You could see without their core shell structure, it decayed rather quickly, and with the core shell structure, it hung up around just under 750 milliamp hours per gram, which is quite good for tin. And the notion, as you can see, is that you have an outer carbon shell. Now, we know carbon passivates by an SEI layer, so it adds this terminating passivation layer to the tin that protects it from further degradation with the solvent. And then inside, the active material is the tin, and it's protected then from the electrolyte reactions. There's a similar bent of work going on by Chui and co-workers out at Stanford. And in their case, the green box is the preferred system that they went to. The conventional system is shown on the top, where you just take pure silicon, you charge and discharge it, you keep getting this SEI growth, And this large gray region is this very thick SEI. When you get that thick, it's a bunch of lithium adducts and basically junk that forms on the surface. And what they did then instead was to say, I'll have a hollow lithium region in the core. That allows me for mechanical expansion into the core, so some stress relief. And then over that silicon, I'm going to oxidize with a flash oxidation of silica, so SiO of some form, SiOX. And now that tends to help hold things together. It acts like an artificial solid-electrode interface. The growth of the actual solid-electrode interface or lithium reaction products, solvent reaction products, is not excessive. So as you charge, you can see that it swells into the core center, and finally as you discharge, you get back a geometry that looks a lot like the original geometry here, and with some discharge reaction products on the outside. Now the other thing is, because they're using extremely small geometries, the characteristic resistance to lithium diffusion is very small, and they could get very high rates in these systems. And so a 12C rate means they discharge the battery in a very short amount of time, and 10 minutes or so for full discharge and charge. And they're maintaining their capacity at this very high rate at a fairly significant value, about 600 milliamp hours per gram. And their current efficiencies are generally quite good, although you can't resolve whether it's 99% or something higher. This is where a log scale would help out. These are some of their AC impedance results, and the point is that they're very stable. And when you look at this, and for those who work in this domain, they would tend to look at that and say it's a very stable electrode structure. And so it's quite promising in this short core shell configuration. And here's another example of some core shell work, and it's a review paper on this material. But basically, again, they're showing this enhanced cycling stability, in this case of a silicon-silica system. And it's more in a conventional processing that you might actually do for high-volume manufacturing. There's a lot of work in these types of systems. In fact, state-of-the-art is actually better than this, but I haven't seen the chemical companies that are getting better than that actually publish some of these results. So to summarize the work then, the top part is more about Gen 1 systems and what we've learned, and also some context for automotive. And I won't review it, I'll just mention it for you there. And then the bottom part of this slide, as far as the summary, is going into things that we might see more in the future. I think we'll see more of these core shell structures enabling these Gen 2 and Gen 3 systems. And I think high-precision coulometry is going to be really important for both accelerated live tests in the future, but also just for characterizing the materials that are made to find out if they have viability. So I'll be happy to answer any questions now. Thank you.
Thank you so much for that very wonderful talk, and it's now open for some questions. Right.
Is the efficiency of silicon the primary reason it's not being used?
You could look at it that way, yes. It also can just plain fail outright, independent of the gradual reaction giving rise to current efficiency problems. Detachment and decrepitation can be rather massive in a silicon system. But when you look at the early work by Cui at the Stanford group, they came out by stabilizing the mechanical decrepitation by going to small particles. Very small particles, when you get, say, 10 nanometers or so, the surface atoms start to dominate, and the particles tend to be more stable, and they mitigate some of the decrepitation problems. However, you exacerbate reaction with the electrolyte then, because you got high surface area. So what they did next was to go to this silica termination, which was quite promising. So you might argue that for small structures, which might be viable for application, the mechanical problems maybe are quite manageable. You have to take advantage of the size effect. You still have that current efficiency then. That's probably the next thing to go after.
So in any of these systems, particularly when you look at packing and the effect of thermal management, does an aqueous system make it into the contenders?
Well, if the metal or batteries could work, yes. So aqueous systems have better thermal conductivity. Now, the aluminum current collector in these systems, if you just think about it, you're stacking up these cells, and the aluminum current collectors are quite good at removing heat, and that's kind of how we get the heat out of the cells, really. But there are a lot of advantages of aqueous systems, in particular the lower cost, and they have much better low temperature performance if they don't freeze. So, and usually with the electrolytes that are used, they don't have that problem. So we'd all like to see aqueous systems work with the kind of energy densities that we see reversibly in lithium-ion systems. So far, it's been a real challenge. You would know more about this than me.
Actually, hold on.
So do your current lithium-ion battery systems work in colder climates like the upper Midwest and New England, or what kind of considerations do you have to
short
take?
answer is yes, but it's a challenge. I mean, we wouldn't sell the vehicles if they didn't, and we have to sell them throughout. Actually, in the case of the Volt, it's sold in Europe and it's sold in North America. So we very much had to make sure that the rule in automotive is GM adheres to it strongly, and it's not a federal rule or anything, but the rule we have, and most companies have this, is that at minus 30 degrees centigrade or above in temperature, no customer needs to have assisted start to drive away with their vehicle. Now, if you go below minus 30 degrees centigrade, which is really cold, then you have a block heater for conventional engines, or you have some assistance in order to get the vehicle going. So when I say work, yes, at minus 30 degrees centigrade and above, they all will perform their functionality. And that's what sizes batteries in hybrid vehicles, the minus 30 degrees centigrade requirement. That's why they're much larger than they really would be otherwise.
Do you think there's any future in battery chemistries other than lithium ion that use analogous materials like sodium ion or magnesium ion? These are all very theoretical systems right now, but
yeah, industrial research, you typically are looking a little more close, near term, and so very few, with a couple exceptions, very few automotive companies, for example, are looking at such systems. We're always in monitor mode. Magnesium, the argument there is it gets 2 electrons for a very light metal, and that it could be very promising. A lot of people are working that area. A handful of people, I should say, are working that area. A fair amount of money starting to flow to that area. Sodium is more difficult, it appears. Magnesium is quite conductive, and it seems to be easier to make an electrode material out of. So we'll monitor it, but I don't know of anything right now that is particularly compelling in terms of performance.
It looks like the core shell nanostructures have a lot of empty spaces.
Yeah.
Doesn't that affect your volumetric energy density?
Yeah, and I don't know whether they're having a problem getting, TEM or images that really showed a good core shell structure. One way or another, they had a lot of tin in there because you can't get that with carbon. So 800 milliamp hours per gram. I agree that didn't show so well as far as the a pervasive amount of core active material within a protective shell.
Do we have any other questions? I have one more back there. Mike is coming to you.
Coming back to the start of the talk, you talked about starter batteries, and I was interested, are you predicting that, in the future we won't see lead-acid batteries anymore as our starter batteries, something we've almost taken as a given for decades
I get
now?
myself in all kinds of trouble with something like that. I'm working on this myself as much as any other project, actually, on a personal level, because there are so many people going after the high energy density systems, and a lot of the researchers in my laboratory, and I tend to look at this as low-hanging fruit. I mean, I think it's pretty clear to StartStop's going to go across the board, and there are a lot of hybrids on the road today. In the United States, for example, there's about on the order of about 300,000, but we also have a vehicle car park of about much larger than that, and we sell about 15 million vehicles a year. That 15 million, I think, in the future, 3 to 5 years, could all be start-stop. I think it could be a real problem if we don't take care of the customer, and so I think that's going to happen. I'm maybe ahead of the pack, or maybe I'm chasing the rabbit and there's no rabbit at the end of the chase. I'm not sure.
Just to follow on there, so is the LTO LMO system going to displace lead acid entirely as a starter?
Well, that would be the idea. I like the idea of a single battery solution. What instead happens is people use a 2-battery solution in a DC-DC converter. So now you've taken something that would really be cheap normally, and you've added a whole lot of cost. So I would rather have no DC-DC converter. The other problem with the DC-DC converter you've got to be careful with is you need to add some logic. Which battery do you charge when? And so that gets kind of tricky. A single battery solution is really simple. And so I prefer a single battery solution for these systems. I think it's better for life of the vehicle also. Upsize the battery a bit to make sure you hit end of life requirements and have a much simpler system. So I think it helps your quality, reliability, durability.
So actually, since we have a couple minutes, I'd like to ask a question sort of on the same point here. Sorry. How about recyclability in some of these things? So one of the key things with lead acid batteries is very nice is that, you know, they tend to be very recyclable. They can be, you know, taken apart and recover the lead. Lithium tends to not be that much. So how do you see the impact on that side?
Well, lead acid battery points to the fact that if everybody gets behind something, you can really recycle something because there's not a good financial incentive. Lead acid is, you know, those are cheap batteries. The reason they're recycled is because the industry got behind it, the government got behind it. We all realize we don't want lead out in the environment. So it's a highly recycled item. Current lithium-ion batteries, the good news from a recyclability point of view is they got too much cobalt in them. So that's why they cost so much, cobalt and nickel. But recyclers are willing to take them because they can make money on the cobalt and nickel. Now, a really good question is, what happens if you come out with widespread lithiated graphite lithium iron phosphate? The iron phosphate, it's expensive to manufacture, but once you have it from a recycled product, you don't get a lot of value out of it. So then I think we're going to have to work hard as an industry to set up the logistics around the recycling chain. So it is something that, you know, we have concern over. We have people who are dedicated to program control and logistics associated with recycling of batteries.
On more of the business side of things, you said you partnered with groups at Stanford. I saw you were partnering with groups at Shanghai University. Wow. I was wondering if there are Chinese companies who are interested in the same research and if you're partnering with them at all, if there's any sort of cooperative agreement, and or maybe just through universities.
There's a whole lot of, it's hard for me to keep track of all this stuff, but there's a whole lot of collaborations that go on. And you know, that you can argue the best minds weren't all born and live in the US, and so you want to work with the best minds around the world. So the short answer is, yeah, there's a lot of collaboration going on. In GM with other entities and other companies do the same.
Any companies in particular?
Any companies we collaborate with?
Like in China, are there any that come to mind?
Well, I mean, there are big companies there, like Lithium is a very large manufacturer. And I don't want to talk about who we collaborate with specifically, but there are plenty of battery companies in China to collaborate with if that's your band. There is one thing you have to be careful of. There are export control laws, and there's a limit at 300 watt-hours per kilogram. And when I talk about Gen 2 and Gen 3 batteries, that precludes such collaborations with certain countries. And so what you have to do if you want to do such collaborations, you have to go to the Department of Commerce, and you have to get an export control license. And that's a whole nother, I don't want to get into this topic right now, but it's a whole nother element in the whole business landscape when you talk about high energy density batteries.
Question up here.
If loss of lithium is the life-limiting thing, is there any way to get lithium back into the battery and recharge it?
It's a good question. There's so many patents in that topic. And you know, maybe some sort of flow arrangement or the problem is these batteries, right now, the current configurations, the batteries are hermetically sealed. And to try to pull them apart and be able to get to the active materials, not disrupt them too much, and get it all back together has proven to be very difficult. Whether that could be done in the future, it seems compelling. Could you have a reprocessing plant where you have batteries come in for vehicles reaching end of life and reprocess the electrodes and reuse instead of recycle? I think there's a good possibility of that. To date, it's been something people have looked at, but no immediate solutions have really jumped out. In the lab, for what it's worth, we do it all the time. We just take a cell apart and we test, you know, put more lithium in, and it starts working, you know, again. And so that's easy to do. In industry, it's a little harder to do with a product.
From an academic point of view, is it a fool's errand to try to pull the lithium out of the SEI to reduce the SEI?
No, it might be. I mean, you think about it. Maybe you could add an electrolyte additive to a spent battery that makes the lithium more accessible. You might even try to, you know, add something that, if the lithium is in a reduced form, oxidizes it and then subsequently plate it out. Something like that might be doable. Don't know. Yeah.
Well, it looks like we're just about to the end of our time. I want to thank Mark again for...
Thanks.
We have a small reception right outside, so please join us. Thank you all for coming.